Hi guys, imagine you are trying to analyze the relationship between advertising spending and company sales. You collect the data from 100 companies. Everything looks reasonable. Then you add just one more observations. Suddenly, the regression line rotates. The slope changes dramatically. Your forecast changes. Your investment conclusions change. How can a single data point have that much power? This is one of the most important ideas in regression analysis. Professional analysts never trust a regression model without asking one simple question: is one observation driving the entire result? Today, we are going to learn how professionals detect these influential observations using leverage. Studentized residuals and briefly cookie. More importantly, you will understand why these measures exist and how they protect you from making poor investment decisions. So, why influential observations matter? Before learning the formulas, let's understand the problem. Regression is designed to find the relationship between variables. For example, how do interest rates affect house price? How does GDP growth affect corporate earnings? The regression line represents the overall relationship in the data. But regression assumes that all observations contribute reasonably to that relationship. Sometimes that assumption breaks. One observation can pull the regression line toward itself. Think of the regression line as a mental ruler lying on the table. Most data points generally support the ruler, but one very heavy object placed at one end can bend the ruler in each direction. That is exactly what an influent observation does. It changes the estimate coefficients, it changes predictions, it changes statistical significance, and ultimately it can change an investment decisions. That is why professional analysts always check whether a regression result is driven by the overall dataset or by just one unusual observation. Now, here is the key idea. Not all unusual observations are unusual in the same way. There are two completely different possibilities. The first is called high-level response. The second is called outlier. Let's separate them. A high-level response had an unusual value of the independent variable x. It made that most companies spend between $5 and $20 million on advertising. Then one company spent $500 million. Its X value is extremely far away from everyone else. That observation has high leverage. Notice something important. Its Y value might actually fit the regressions perfectly. The problem is simply that its X value is very unusual. Now consider an outlier. Here, the X value looks completely normal, but the Y value is widely different from what the regression predicts. For example, two companies spend exactly the same amount on advertising. Most earn about 100 million in revenue. One company report only 10 million. That company is an outlier. Its Y value is unusual. So remember these simple distinctions. High leverage is about where the observation is located horizontally. Outliers are about how far the observations sits vertically from the regression line. These are different concepts, Sometimes they occur separately, sometimes the same observations has both characteristics. And when that happens, that observations can become extremely influent. So, why high leverage and outlier is dangerous? Now let's combine the two ideas. Suppose an observation had an unusual x value that's already giving it leverage. Now suppose it also has a very large prediction error. In other words, it sits far away from the regression line. Now that single observation is pulling the regression line horizontally and disagreeing with existing relationship vertically. The result: the regression line may rotate dramatically, slope coefficients change, intercept change, predictions change, even hypothetic tests may change. This is exactly why influential observations matter. They don't simply look unusual, they actually change the model, and that is the key distinction. An observation can be strange without being influenced. Influence depends on whether removing that observation materially changes the regressions. So, how do we measure leverage? We use something called the leverage statistic, written as XII. Intuitively, leverage measures how far an observation X value from the average X. Think about a classroom. Most students score around the class average. One student scored far above everyone else. That student stands out. Leverage matters the same idea, but for the independent variable. A leverage value is always between 0 and 1. The closer it is to 1, the more unusual that observation's X value is. So a commonly used rule of thumb is XII greater than 3 times k plus 1 over n, where k is the number of independent variables and n is the sample size. If an observation exceeds this threshold, it deserves closer inspections. Notice the wording carefully. It is not automatically influential. It is simply a candidate for further investigations. Now let's detect observations that don't fit the regression line well. We start with the residual. A residual is simply actual value minus predict value. Large residuals suggest poor predictions, but here's the problem. Residual naturally varies. Some observations have larger variability than others, so comparing raw residual isn't fair. Instead, we standardize them. That gives us the studentized residual. Okay, EI star is the residual with the ith observation deleted. XE star is the standard deviation of the residuals. K is the number of independent variables. MSE is the mean square error of the regression model that deletes the ith observations. HII is the leverage value for the ith observations. Think of this exactly like a t-statistic. Instead of asking how large is the residual, we ask how large is the residual relative to the amount of variations we normally expect. The calculations remove one observation from the regressions, re-estimates the model, calculate the predictions error, then divide that error by its estimate standard deviations. The result is a standardized measure. If the absolute studentized residual exceed the critical value from the t-distributions, that observations is considered a potential outlier. This approach is much more reliable than simply looking at raw residuals because it accounts for difference in variability across observations. Historically, analysts also use another measure called Cook's D. Instead of looking only at leverage or only at residuals, Cook's D adds more direct questions. What happens to the regression model if we completely remove these observations? If deleting one observation cause the regression coefficients to change substantially, Cook's D become large. The EI is the residual for observation E. MSE is the mean square error of the estimated regression model. If DI is greater than 1.5, the I observations may be influential and merit further investigations. If value above 1 often indicate a highly influent observations. So today we look beyond regression equations and focus on something professionals never ignore: the quality of the data behind the model. Thanks for watching.